Right. Morning again. This is our second session, and we're going to continue with number theory. Right. Last week, what we looked at was mixed numbers. Sorry, not mixed numbers. Mixed operation involving integers. We did this exercise to close off class last day. Numbers 1 to 12, and I shared the solutions in the Google Classroom. Today we're going to continue the topic. This is part 2 of the topic. We're looking at laws today, different types of laws involving our whole numbers, integers, right? The commutative law, associative law, distributive law. Basically, you just need to have an understanding of what these laws are. I have some homework for you to complete on the whiteboard here. This one you'll be doing inside your notebooks, and you'll upload it to the Google Classroom. We look at two more rules, which is the identity elements for addition and multiplication, and inverse elements for addition and multiplication. After which we're going to look at some fractions, decimals, and percentages questions. That's going to involve converting between each. So fractions to decimals, decimals to fractions, and then we look at percentages. We have an exercise, an in-class activity that we will do. And once we get through with this, then we could look at our next topic, which is indices. We're going to look at some operations involving indices. All right, so that's what we have planned for today. So I'm going to get started with where we left off last week. Right, so we're going to get started now. So first off, we're going to talk about some laws that pertains to addition and multiplication. All right. So those of you just joining in, just to recap briefly, we're just about to start, and we're going to be looking at some laws involving addition and multiplication, namely the commutative law, the associative law, and distributive law. These things you guys would probably know innately already, just probably not by name. All right. So the first one we're going to talk about is the commutative law. Have you ever noticed that when we add numbers together, the order in which we arrange these numbers does not affect the answer? For example, if I have 2 plus 3, if I write this as 3 plus 2, as you'd see here in my examples, right, I will still get the same result. So that property is what we refer to as commutativity. The law is the commutative law, right? You'll bite your tongue when you've seen it. Commutative law. So the commutative law says that for addition and multiplication, regardless of the order in which you perform the calculation, you will have the same result. It's the same for multiplication as well. So order does not matter for addition and multiplication. And the name of that is the commutative law, right? Or the adjective to describe that is what we call commutativity, right? Order of addition / multiplication does not affect the answer. Right? It doesn't affect the answer. Everybody okay with that? So regardless whether we multiply 7 multiplied by 5 or we do 5 multiplied by 7, it's still going to yield the same result, which is 35. The same thing happens for addition. If I have 2 plus 3 plus 1, that's the same as 3 plus 2 plus 1 is the same as 1 plus 2 plus 3. All of them is going to give me 6. So order does not matter. And the word to describe that is called commutativity, right? Or the commutative law. So when you see that being described, or you see that property, this is what you're going to describe it as, commutativity. For subtraction and division, however, this rule does not apply. It doesn't hold for subtraction and division. The order matters for subtraction and division. So subtraction and division are the opposite of addition and multiplication. They're said to be non-commutative. If we change the order, we're going to get a different result. So for example, if I have 6 plus 4, sorry, 6 minus 4, I am going to get 2, right? But if I have 4 minus 6, the answer is going to be negative 2. Similarly, if I have 18 divided by 3, that's going to give me 6. But if I change the order of that and I have 3 divided by 18, then I'm going to get 1, 6. So these are non-commutative, right? They're non-commutative. The order matters when we are multiplying or dividing. All right, everybody okay with that? Associative law now. The associative law, right, looks at, again, addition and multiplication. So the associative law has to do with brackets. And for addition and multiplication, it does not matter where we place the brackets. All right, it doesn't matter where we place the brackets. If we place the brackets, in my example here, I have 4 plus 3 plus 2. If I bracket 3 and 2, right, I'm still going to get 4 plus 5, which is 9. If I place the brackets in front and I put 4 plus 3, you know what, we're supposed to work out the brackets first. Then I'll get 7 plus 2, and that's still going to give me 9. So this law, called the associative law, says regardless of where we place the brackets, when we are adding and multiplying, our result is still going to be the same. Here's an example with the multiplication. 3 multiplied by, open brackets, 4 multiplied by 2, right? Our rule says that we're supposed to work out the brackets first. So 4 2s are 8, and then we multiply 8 by 3, and we're going to get 24. If I move the brackets from there and I put 3 multiplied by 4 in brackets, and then multiply by 2, 3 4s are 12, and 12 multiplied by 2 is still going to give me the same result, 24, right? We could also remove the brackets entirely, and that still does not affect the answer. If I remove the brackets entirely, 4 plus 3 plus 2 is still going to give me 9. And if I remove the brackets here, 3 multiplied by 4 multiplied by 2 is still going to give me 24, right? So the associative law and the commutative law is for addition and multiplication only. For the commutative law, basically, we say that order does not matter. It doesn't matter the order in which we add or we multiply numbers. Our answer will always be the same, right? The associative law says it doesn't matter where we place the brackets. Once we add in and multiply, regardless of where we put brackets, the answer is going to be the same. Now, if I throw a minus somewhere inside of here, right, or a division somewhere inside of here, that changes everything. The associative law will not be applied there anymore, because for subtraction and division, right, where the brackets are matters, right? Take, for example, here. We have 7 minus 5 plus 6, and the 5 plus 6 is in brackets. And then underneath here, I have 7 minus 5 plus 6. Could you guys work out the answer for this one for me and this one? And let's compare answers and see if it's the same. Let's check and see if it's the same. Remember, when we work in these, you always do the brackets first, right? So in this first one here, you want to add your brackets first here, and then subtract the answer you get from the brackets from 7. This one, we do the brackets here first and then add the 6, right? What you'll notice is that the answers are different, because here, just as I mentioned before, it's not all addition and it's not all multiplication. So this associative law that I'm talking about does not hold for these circumstances, right? If it's all addition, all multiplication, then it don't matter where we put the brackets. It don't even matter if we have brackets. Yeah? So what you'll get for this one? 7 minus, open brackets, 5 plus 6. Do you want to share the answer with me? Use your mic. 7 minus what?
Negative 4.
That's correct, right? We will get 7 minus 11. And because the 11 is bigger, we're going to keep the sign of the larger number and then subtract 7 from 11. Right? So anytime we're working out addition or subtraction, right? Remember the 7 is a positive 7. And the signs are not the same. First, we need to work out what our sign for the answer is. What is the sign? The sign is going to, we're going to keep the sign of the larger number. So if I compare the number 7 and the number 23, 23 is larger. So I am taking this sign from in front of the 23 for my answer. After I do that, I'm going to subtract the smaller number from the larger number. So 7 from 23 is going to leave me with what? 16. Negative 16, right? That's how it looks, something like that. And with this one here, if I change where the brackets are, look at what happens. 7 minus 5 now is going to leave me with 2 plus 6. And 2 plus 6 is 8. So the answers are totally different. So the rule of the associative law rather does not apply to subtraction and division. So once we throw subtraction and division into the mix here, here I'm adding subtraction together with the addition. Here I'm adding division together with the addition. It changes, right? If we move around the brackets, if I change the brackets, then I'm going to get a totally different answer. So here, 6 plus 9, that's going to give me 15 divided by 3. That's equal to 5. But here, this is going to be 6 plus 9 divided by 3 is 3. And that's going to give me 9. So two totally different answers. And the reason for that is because we have division inside of here. If I had 6 plus 9 plus 3, it doesn't matter if I add 6 and 9 first, or I add 9 and 3 first, or I just add all of them together. Addition throughout means that the associative law will hold, and the brackets doesn't change the result. Where I put the brackets doesn't change the result. Everybody understand that? Just drop a 1 in the chat board if you do. Everybody good, right? Nikolai, Misha, good, Siobhan, Sabira. Tyrese, you okay with that? Right, so brackets doesn't affect the answer we get, and the order in which we add or multiply numbers doesn't matter. Right, once we are adding and multiplying, order doesn't matter. Distributive law now. So if we have something like 2 open brackets 5 plus 3, we could say that multiplication could distribute itself over addition. If I give you some test papers and I tell you distribute this amongst the class, and you have a stack of test papers or question papers rather for a test, you're going to hand out, distribute it to each individual in the class. When we have a question like this, and we have a number outside of our bracket and something happening inside of the bracket, the 2 is distributing itself amongst everything inside of the bracket. That's just like if Subira is handing out the question papers inside of the class, right? She will give each person a question paper. So that's how you have to think about it. So 2, right, could be distributed across everything in the bracket, meaning that we could multiply everything in the bracket by 2. Right, so 2 4s is 8, 2 1s is 2, and we'll get 10, right? We could also work out the bracket as we used to before. We could say 4 plus 1 is 5, and we know that brackets means to multiply. So 2 multiplied by 5 is going to give me 10. Here we still distributing it 2 by what we have in the bracket, right? So when you see this distributive law, we say that multiplication could distribute itself over addition. All right, everybody understand that? Yes? All right. So for homework, you guys are going to do numbers 1 to 10. Right? Basically, what you'll be doing here, so just make a note of the homework somewhere. I will make a note of it too. So today we did so far associative law, commutative law, distributive. I'll post the homework. I'll cut it out and post it in the Google Classroom. For homework, we have 1 to 10 on associative, commutative, or distributive. Right? I remember I would send you guys these slides in PDF via the chat and in the Google Classroom. All right, the link to the Google Classroom is in the group. If you didn't get the link to the Google Classroom, just private message me. All right. Send me a WhatsApp and I'll send you the link for the Google Classroom. All right. So these are gonna be for homework. I will send it in the group. Actually, I'm gonna do that one time. Forget. All right, so I need to. Nice. Being proactive. Good. So some more rules. The other thing that we're going to look at is what we call identities for addition and multiplication. Basically, identity elements are numbers that when added or multiplied by another number is going to give you back the same number, right? That's straightforward. The identity for addition is 0. If you add 0 to anything, you're going to get back the same thing you started with. It will return itself. So 4 plus 0 is 4, 13 plus 0 is 13, negative 5 plus 0 is going to give you back negative 5, negative 17 plus 0 is going to give you negative 17. So 0 is the identity for addition. Anything added to 0 is going to give itself the same number. For multiplication, right, the identity is not 0, but 1. Anything multiplied by 1 is going to return itself. So 4 multiplied by 1 is going to give us 4. Negative 3 multiplied by 1 is going to give us negative 3. Right? So our identity elements for addition, and just scribble it here, identity elements for addition is the number 0. For multiplication, it's the number 1. Right? So anything multiplied by 1 will return itself. Anything added to 0 will return itself. So this is just things you need to know, right? They're not really gonna ask you a question on, you have to work out something, but you just need to general knowledge. You need to know these laws, right? You see them in algebra, and you also need to know these identity elements. From time to time, it may come in a bit useful. So the other one is inverse elements. So for addition, you're looking at a number that when you add it to your starting number, you're going to get the result of 0. So how can you get 0 from adding a number to another number, right? So usually the inverse element is really just the opposite of the number, meaning the positive or the negative of the number. So if you start with a positive 4, the inverse of positive 4 under addition is negative 4. It is the number that when added to this number is going to give you 0 as an answer, right? So the inverse for addition is always the opposite sign of the number. So if I tell you what is the inverse for 13, it's going to be negative 13. If I ask you what is the inverse for negative 15, it's going to be positive 15. All you are doing is just changing the sign on the number. And what that results in, or how you can check to make sure that you have the correct inverse element, is that when you add the two numbers together, you should get 0. right? Positive 13 plus minus 13 will give me 0. Negative 15 plus 15 will give me 0, right? Everybody all right with that? Drop a Y in the chat board if you're okay with that one. Right, so notice with the examples, all I am doing is just changing the sign. Inverse of 4 under addition, -4. Inverse of 3 under addition, -3. Inverse of -4 under addition, opposite sign, +4. Inverse of -3 under addition, well, this shouldn't be +4. This should be +3. Right? Good. Multiplication now. The inverse of a number and a multiplication is by flipping the number. Right? So if we start with 4, right? If we start with 4, the inverse of 4 under multiplication will be a quarter. If I start with a quarter, then the inverse under multiplication is going to be 4. All you're doing is really flipping. Remember, 4 is the same as 4 over 1. So for the inverse, what we are doing is we are moving the 1 on top of here and moving the 4 underneath here. So the inverse is going to be a quarter. Right? If I have 2, 6, the inverse is going to be 6 over 2. 6 going on top, 2 going below. Now, how can you check the inverse? Under multiplicative inverse, when you multiply the two numbers by each other, you should get 1. Right? You should get 1 when you multiply the two numbers by each other. Everybody okay with that?
So
So let's try if I have something like 5. The multiplicative inverse of 5 is going to be 1/5. All I'm doing is I'm rewriting that 5, right? Remember, 5 is the same as saying 5 over 1. So the multiplicative inverse, right? Multiplicative inverse is going to be 1 over 5. And if I started with a fraction like 3/4, then the inverse is going to be 4 over 3. Right? How you could check it? Multiply both numbers by each other, and you should get 1. These would cancel, these would cancel. You get 1 same. Yeah? Everybody okay? Everybody all right with that? All right. So let's get some practice. So you just have 2 questions. You want to work out these quickly for me. 1, the inverse of 4 under multiplication, right? And 2, 6 plus 0 is equal to 6, so 0 is what? So you're just answering these. You tell me either A or B. You can put the answer in the chat board. That's fine. Opening up the chat board there. So everybody just put your answer in the chat board. Just put 1, like right in the chat board. 1, and if you think the answer is A, you put A. 2, if you think the answer is B, you put B. Right, so write it like that. Right, so the multiplicative inverse of 4 under multiplication is going to be C, a quarter. Right, remember, for the multiplicative inverse, if you can see the example up here, all you're doing is you're changing, right? You're flipping the number or the fraction. A whole number like 4 could be written as 4 over 1. So the multiplicative inverse, I'll just put MI for multiplicative inverse. I come kind of graphic for them. Right? It's going to be 1 over 4. You're flipping it. Yeah? Everybody okay now? 6 plus 0 is equal to 6. So 0 is not a member of the set of integers, the identity element under addition, the inverse under addition, and the inverse under multiplication. But the correct answer for that one is going to be B. I'm not doing it. It's going to be B, the identity under addition. The identity for addition is always 0. So 0 added to any number is going to return itself. So number 2 is B. Everybody all right with that? You sure you're good? Malachi, understand that? Nikolai, understand it? Yeah? Siobhan, you're good, right? Right, Siobhan had both answers, correct. Sabira? Tyrese, you understand now?
Yes,
Yeah?
sir.
All right, nice. Good. So we're moving on again. So next thing we want to look at is our fractions. I'll just expand this a bit. Here. Everybody see now clearly? Right, so let's talk about changing between fractions, decimals, and percentages now. So I have some examples here on the screen, right? First, we're going to talk about changing fractions to decimals. Basically, when you want to change fractions to decimals, we divide the numerator by the denominator. So here's the example. They have 3/8. So the numerator, this is your numerator here on top. That's 3. 3 is being divided by 8. And we think about it the same way when we're writing some division questions as well too. So if I put 4 over 8, I am dividing 4 by 8. If I have to write this using a division sign, this is what I'll be writing. I'll be dividing 4 by 8. The bottom, look at the bottom number. The bottom number is what we call our divisor. Remember this from primary school? This is our dividend. And what is called the answer? The answer is a quotient. Remember that? No? Everybody forget that from primary school? Michelle, remember that? No, you forget that. Sabira. You don't remember that? Malachi. What was your teacher? Your teacher name? Mr. Issa then teacher la? Malachi and Sabira. Siobhan, you remember that? Yeah? Alright. Tyrese and Nikolai. You remember that from primary school? No, forget. That's alright.
Yes, sir.
Tyrese remember, you see? I know I'm not crazy. So the numerator, right, is the one that's going inside of our or under our division sign. The denominator is what's going on the outside. What we have on the inside here, we refer to that as the dividend. The number on the outside is the divisor. That's what you're dividing by. So it's like you're saying you're taking 3 and you're breaking it up into 8 parts. That's what you're saying basically. The answer you get is what we call the quotient. So sometimes you might see a question that tell you, find the quotient of 3 and 8. So what you're doing there basically is you're dividing 3 by 8. Nevertheless, if we want to convert a fraction to a decimal, right? We take the fraction, let's say we have 1/5, and we want to convert this into a decimal, right? What am I going to put inside of here? Tell me. Can you see Mike? What you put inside of there? The 1 or the 5? Look at the question here with the 3 8s. Which one went inside? The 3 or the 8? Anybody? Markai, which one went inside of the division, under the division sign? The 1 or the 5? What I put it inside of here?
Dividend.
Right? But what number is the dividend? The 1 or the 5? 1. Very good. Very good. And what's going on the outside? The 1 or the 5? Well, we already used the 1. So what remaining? The
5.
The 5. Now, when we have to divide this, 1 can't go into 5. So this is how the decimals is coming to play. Right? So we keep adding zeros to the right until we could actually work this out. Until you can no longer divide this again. So what you do first is you put a 0. 5 into 1 cannot. You put a 0. Then you put a point under point. Then you add a 0. Now we say 5 into 10. You treat it as a whole number, even though you have the point there. Right? What is 5 into 10? Did 5 go into 10? Yeah. How much times? 2 times. Very good, Nikolai. 2 times. And then long division. 2 multiplied by 5 is 10. You subtract them and you get 0. So what you're trying to do is basically end up with a 0 here. You're going to continue adding zeros until you can't divide anymore. You want to get to the point where 5 divides this number that you've been adding zeros to exactly. So converting 1/5 to a decimal is equal to 0.2. Everybody understand that? Yeah?
Yes, sir.
Let's look at another one. Let's say we have 3/4. I want to change that to a decimal. Which one I put in on the inside here, the 3 or the 4?
The 3.
The 3, good. Right, and if I put the 3 here, that means I put in the 4 on the outside. So I'm going to put the 3 here. But could 4 go into 3? No, it can't. So that's where we start by putting the 0. We're going into the decimals now. Then we would say we add another 0 here. Now 4 could go into 30. That's a big enough number for 4 to go into. And how much times 4 will go into 30? Well, we have 4, 8, 12, 16, 24, 20, 20, 24, and then 28. 7 4s is 28. So I write 7 here. 7 by 4 is 28. Now remember, you're treating this like normal numbers, even though you have the point there, right? 30 take away 28, now going to give me 2. I don't want a 2, I want a 0. You have to continue dividing until you end up with 0 there. So what we do now is we add another 0 here, and you bring down the 0. So now you'll say 4 into 20. Could 4 go into 20?
Yes, sir.
Yes, it could. 4 into 20 is 5.
5.
Right. 5 4 is now going to give me 20. Then I subtract. 20 subtract 20 now is 0. Now I could stop. So you see, 3/4 in decimal is 0.75. See that? You try one for me now. Try 3/5. What's going to go on the inside? In here, the 3 or the 5?
3.
3. And 5 going to go here. Right? I remember to start this, you'd say 5 into 3 can't. So I'll put a 0. put a point, and you add a 0, and then you start to work from there now. 5 into 30. Finish it up for me. All right, so what answer you got for that?
0.6.
0.6, right? Because 5 into 30 is going to give us 6. And then we do 6 by 5, that's going to give us 30. We subtract that, we get the 0 that we're talking about. Right? Very good. Good job. So I have a few more questions. We will do these here as yet. Keep getting to the steps. We'll get to this afterwards. There we go. Everybody can see this? It's big enough. So I want you to try this for me. It's the same thing that we just did. So for example, if you want to convert 4/9 into a decimal, right? What you're working, the 4 is going to go on the inside. The 9 on the outside. Right? 9 can't go into 4, you put a 0. 9 into 40. Right? Could 9 go into 40? Yes, it could. 4 times. 4 nines are 36. Right? Now, sometimes you might realize that I'll do this one, right? As an example. 40 take away 36 now going to give more 4. Not so? I'll put a 0 again, I'll bring down the 0. Again, another 40. 9 into 40 now going to give me what? Same 4 again. 4 by 9 is going to give us 36. But we back to the same thing. 40 take away 36 going to give more 4. I'll put another 0 again. I'll bring it down. If after 3 times you realize that you're continuously getting the same thing, this is 4 here now. This is what we call a recurring decimal. It means that no matter how much we continue to do this, it will continue giving us 4, 4, 4, and like that going on. And what we do is we just put some dots after it, right? Because that's not going to change. Every time you multiply 4 by 9, you're going to get 36. When you subtract the 36, you're going to get 40. If I go one more step again, right? Look at it. I'll bring down our next 0, right? I'll still have to use 4 9s at 36 again. I'll get another 4. And we could go on like this from now till next week. We'll continue getting 4s. So in an instance like that, you will say 4 9s is equal to 0.444, and then you put dot, dot, dot. So it recurs. Another example of that is a third, right? A third will be 0.3333 like that going on till 2/3 is going to be like that as well. That'll be 0.66 and continue like that going on and on and on. Right? So when we divide fractions to get a decimal and you are repeatedly getting the same number when you divide, we call that a recurring decimal. All right, and after about 3 attempts, you put dot, 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 so that the examiner or your teacher knows that, okay, it's a recurring decimal, he's going to continue getting that same number over and over. Everybody understand that? Yeah? All right, so you're trying these 10 for me. So I did 1. You're going to do 3/8, 5/7, 2/3. Remember what I tell you about 2/3, 7/12, 5/11, 9/11, 6/13, 1/5, and 8/15. All right, everybody okay with that? You all understand the recurring decimal? Yeah?
Yes, sir.
All right. So let's look at these. So we saw how to do number 4 already, right? Number 1, sorry, number 1 was recurrent decimal. Right, a recurrent decimal.
I can't call 911. If I call,
Right, 9 into 4. Another 4. Right, and we'll continue like that. So the answer for this first one was 4 over 9 is equal to 0.444. Number 2, we had, this was in our example, 8 into 3 is 0, 8 into 30, right? 3 8s are 24. Right, that's going to leave us with 6. Add another 0, bring down the 0. 3 into that, that's going to give me 7. 7 hits are 56. 4. Add another 0, bring it down. 8 into 40 is 5. 0. So our answer 3 8 is equal to 0.375. Yeah. So to push these down a bit. Right, 3. We have 5 7, so right, 7 into 5 cannot. The other 0, 7 into that is 7, 7 by 5, 7 by 7, sorry, it's 49. Move it to 1, bring down another 0. 7 into 10 is 1. Get 3, bring down another 0. 7 into 30, 3. 3 7s are 21. Subtract, we get 9. Add a 0. 7 into this 7 by 8, 7 by 12 is 84. And 7 by 13 is 91. So you go with, sorry, I didn't need to bring a 0. My bad. 7 into, I'll put it right. 7 into 9 is 1. 7 could go into 9. Oops. Rubbing off everything. Right, good. 7 into 9 is 1. We could do that there. 1 7 is 7. So I didn't need to add a 0 there, right? To this remainder that I get. And then 9 take away 7 is 2. This is where I add another 0 again. 7 into 20 is going to give me 2. 2 7s are 14. Right? Subtract again. 20 take away 14, going to leave us with 6. Add a 0 again. 7 into 60. Right? That's going to give us what? 8. 56. At some point in time, we're going to have to 2. So otherwise you'd be going on and on and on like this. Another 0. 5. 50. You go again, 7. Right, so this should be a long number. So you could stop there. I wouldn't go any further. Right, so 5 sevens usually. What I should have done is tell you to write it to a certain amount of decimal places. You get 0.71312885. Anybody got as far as doing this, or you all went all the way? Anybody went further than this? Yes, no, no, yes.
No, sir.
No, sir.
Okay. Right, if you have at least up until 0.7131 or 132, that's good enough. Everybody understand that one, right? 2/3, remember 2/3? 2/3
Yes,
is
sir.
another recurring decimal.
0.
Yeah, that's correct. We'll continue getting these. Right, you continue getting this. So 2/3 is a recurring decimal, so you could write it like 0.666 and just put your dots. Yeah. Number 5. It's going to be number 5 right here. 7/12. Zero into 70. 5 12s are 60. 6 12s are 72. So you could use 5. That give us 10. 12 into this here, put 0 here, cannot. Then add the 0 now and bring it down. Right, 12 by 8 is 96. And 12 nines are 108. So I went to 40, we're going to give them a 336. Right, and then you end up with a recurring. So you could say 7 over 12 is equal to 0.50833, and that 3 will continue going like that. Yeah? Everybody got that?
Yes,
Yeah.
sir.
Yes? We sure got it. Malachi, Sabira, how
Yes,
about
sir.
you? Nikolai? Siobhan?
Yes, sir.
All right, nice. 6. 511 as a decimal. Right? Sorry. Five in here, 11 here. Right, it is 4. Then we could use 5. 5 11s are 55. Right. 11 into that, gonna give them a 4. 4 by 11 is going to give them 44. Bring down another 0 again. 5. So realize this is another reoccurring. Right. So 5 over 11 is equal to 0.4545, and I'll continue going now. 4 5. Yeah. Also that. Yes.
Yes, sir.
Yes, sir.
If you put the cameras on, I'd see if you shake your head and thing, but with the cameras off, then I'll be waiting on everybody to answer. So we did 7. Number 7 is 911. So we could do 9,
0.82.
what you got for this one?
0.82.
82 only. 88. Eleven into 20 here going to give me 1. 1 by 11 is going to give me 11. When I subtract here, I get 9. Bring down another 0. 11 into 90. Going to give me back 8 again. 8 by 11 is 88. I'll get 2. Bring down another 0. 11 into this going to give me 1. So this is a recurring decimal again. Right? So not, if you're wrong, then the 12 marker will be 0.82, right? So 911 is equal to 0.8181, and you put your dots because that's a recurring. If I ask you to write it to 2 decimal places, then you'll write 0.82. Okay?
Okay, sir.
Number 8. Six 13ths. So the 6 going on the inside, 13 on the outside. Right? 13 by 2 is 26, by 3 is 39, by 4, that's 40, and 12 is 52. By 5, that's what, 50 and 15. 5 will be too much. So 4. 4 by 13, 40 and 12 is 52. When I subtract here, I get 8. I add a 0, I bring down the 0. 13 into 80. 13 by 5, we said, is 50. And 15 is 65. 13 by 7, 70. That's too much. 13 by 6, 60, and 18 is 78. Right. 80, take away that, then I give me 2. Right. 13 could go into this, that'll give me 1. 7, add a 0, bring it down. Right. Into 70. Now we said ours, we could use 5, 50, and 15. 65. Right, and we could go on like this for a bit. This should be 13 by 3, 50 and 9, 39, 4, 40, and 12 is 52. We gotta use 3. We're back to the 80 again. Right? So next thing would be a 6. So we could safely say 6 over 13. We don't want to go continuously, right? I guess something like this we could probably. Usually they would tell you stop at X amount of decimal points. Right? So they might tell you, if they say write it to 3 decimal points, we say to 3 decimal points or decimal places, then we really stop it. We're stopping up to the 3 points here. We're looking at the number after. And if this number is 5 or more, then we will say 0.462 to 3 decimal places. Everybody understand now? Yeah?
Yes, sir.
Last 2, and then we wrap up. 1/5 as a decimal, you also 1/5 before. That's an easy one. That'd be 0.2. Last one for a close off. 8/15. So by 60 is 4, by 5 is 75. Right? By 3 is 45. And we're going to get a reoccurring. Right, we gotta go 3 again. Okay. So 8/15 is equal to 0.5333. Yeah? Everybody okay with that? Yes? All right, guys.
Yes.
So we're gonna wrap up with